Now torque on a current loop and magnetic dipole. So torque on a rectangular current loop in a uniform magnetic field. Now say here, this one is the schematic diagram for that. In exam, you have to draw this one. This is just for understanding. Okay. See, here two magnetic poles north and south produce the uniform magnetic field in the direction as shown in the figure. And in this particular magnetic field, the rectangular current carrying loop, or we can say coil, is placed with the dimensions of length and breadth A and B. And suppose current I is passed through it. At present, the loop is placed in the magnetic field in such a way that the plane of the loop is in the plane of magnetic field. So, the area vector of the loop. So, for any surface, when we represent its area by vector, then its area vector is represented perpendicular to the plane of that particular surface. So we can say the loop is placed in the magnetic field here in such a way that the area vector of the loop is perpendicular to the magnetic field B. Now, let's calculate the forces acting on different sides of this loop. So, if we take the force on this BC side, then BC side, that is with length A, current flowing through it, that is I. So current element, that is IA, it is in the magnetic field B. So force on BC part of the loop, that is IA cross B. But that will be equal to 0. Why? Because IA is parallel to BC here. IA and B both are in the same direction. So theta is 0, sine 0, 0. Similarly, if we think about the force on DA part of the loop, then that is also the current element IA, but here that current element is in the opposite direction of B. It implies that the angle between IA and B, that is pi. So again, this force, that is 0. But now, if we think about the force on this AB and on this CD part of the loop. Up to this one clear? Now force on AB part of the loop. So force on AB, say that is F1. So that is IB, B that is the length of AB part. So current element, that is IB. Now it is making an angle 90 degree with respect to magnetic field. Magnetic field, that is in horizontal direction, and IB, that is perpendicular to it in upward direction. So the force on AB part, that is IBB. Similarly, force on CD part, FCD, say that is F2, that is also IBB sine 90, so that is IBB. But the current flowing in AB part and in CD part, that is in mutually opposite direction. In AB, current is flowing in this direction, in CD, down. So no doubt these two forces are equal in magnitude, but both the forces will be opposite in direction. And here, suppose we consider this type of rectangular loop, then on this particular side, if the force is in this direction, then on this particular side, force will be on this side. So these two forces are in mutually opposite direction and not collinear. These two forces are not acting on the same line. So it will produce the torque. Now, here see, let's represent only those forces. So with respect to reference point, that is the center of the loop. Now, force F1 and force F2 are mutually opposite. And the perpendicular distance between those two forces, that is equal to side A of the loop. So from the center, both the forces are at perpendicular distance A by 2, A by 2. Now, as per definition, torque tau, that is force into perpendicular distance of force from the reference point. So F1 into A by 2 and another torque produced, that is by F2, and that is F2 into A by 2. Now see this, both the forces are producing the torque in such a way that that torque will give the rotation in anti-clockwise direction. It implies that torque produced by force F1 and torque produced by force F2 both give the rotation to the coil in the same direction, and therefore resultant torque, that is the summation of these two torques. Magnitude wise, F1 and F2 both are same, IBB into A by 2, A by 2. So half time IBBA plus half time IBBA. So resultantly you will get the torque, that is I into BA into B. But length into breadth of the rectangular coil will give you area of the coil. So we can write the torque tau acting on the current carrying rectangular coil, or in general now we can say on the coil placed in the uniform magnetic field, that is IAB. And in vector form we can write torque tau, that is IA cross B vector. But this I into A, current into area, that is called magnetic moment of the loop. So we can write in vector form torque tau, that is vector magnetic moment into vector B. Direction of magnetic moment, that will be in the direction of area vector. Okay. Now if your coil or loop, that is made by n number of windings, or we can say n number of turns, then very simple, the torque produced will be n times than this one. So here you have to multiply the equation by n. So in that particular case, the magnetic moment, that will be NIA. Clear to all of you? So magnetic moment, that is NIA, its unit, that is ampere into meter square, and its direction that is in the direction of area vector, and area vector that we have to represent perpendicular to the surface, right? And here we have to fix the direction of area vector again using right hand thumb rule, or we can say right hand screw rule. Okay, we have to place the fingers in the direction of the current and the direction pointed by the thumb, that is the direction of area vector. Clear to all of you? Now if we take the force on AB, so field that is in horizontal direction here, so we can say suppose it is in x direction, then in AB the current is in y direction, the side AB that is B, so force F1 that is IBB, current element and B are perpendicular to each other, so sine 91. Similarly, force on this CD part of the loop, that is also IBB. No doubt magnitude wise this force F1 and F2 both are same one, but the direction of these forces are mutually opposite, as well as these two forces are not collinear. Okay, these two forces are separated by some distance. Okay, there is the separation between these two. Now when these two forces are not collinear, means it will produce the torque. Now suppose here we represent these forces in this another figure. So force F1, force F2, these two are in mutually opposite direction. These two are not collinear. And see the distance between these two forces, that is equal to this side BC and side BC, that is A. So from the center, we can say this portion that is A by 2 and this particular portion that is also A by 2. Now from the center of this one, if the area vector, this one, is represented which is perpendicular to the plane, so perpendicular to this line, and it is making an angle theta with respect to this horizontal magnetic field. So this is the horizontal line. With respect to that, the angle is theta. Now from the center, the perpendicular distance of force F1. So here if this angle is theta, then this will be also theta. So perpendicular distance, that is A by 2 sine theta. Similarly, here force F2, that is also at perpendicular distance A by 2 sine theta from the center. So the resultant torque tau, that is equal to F1 into perpendicular distance A by 2 sine theta plus F2 into A by 2 sine theta, because both the torques produced by both the forces give the rotation in the same direction. So here these two torques are sum up. Clear up to this one? So F1 and F2, that is magnitude wise same one, IBB. So we can write here torque tau, that is IBB into A by 2 sine theta plus IBB into A by 2 sine theta. So half time IBB A sine theta plus half time IBB A sine theta. So we will get here torque tau, that is capital I into B sine theta, but B into A, that is again area. So tau that is equal to IAB sine theta. Here again IA, that is magnetic moment. So we can write torque tau in vector form, that is IA cross B. IA that is magnetic moment, so M cross B. Clear? Now see here, actually this particular theory, if only this one is given to you, then easily you can understand the previous one. See, at present in this theory, the coil is placed in such a way that angle between area vector and magnetic field, that is theta. So we derived this equation. Now the previous theory that we can easily understand with the help of the special case of this one. In first theory we discussed this thing. The loop or the coil is placed in such a way that area vector is perpendicular to the magnetic field. So here if you substitute theta 90 sine 91, then torque that is IAB. In previous theory we discussed that thing. Clear? So easily you can understand from this one also.